Chapter 27 is going to tell us all about current and Ohm's law. So to understand current and Ohm's law, we first need to know what current actually is. So I'm going to draw a little circuit diagram. I'm going to draw my battery picture, and I'm going to have a wire that connects from the positive terminal all the way over to the negative terminal. And I'll explicitly label these terminals while we're getting used to circuits. The longer line for a battery is positive, the shorter line represents the negative. Something that's very important to realize is when I set this circuit up, the objects, the charges that are actually moving, are going to be the negative charges. So I'm going to have negative charges from this negative battery, negative end of the battery, and these negative charges, these electrons, are going to flow around in my circuit, and they're going to be attracted to the positive terminal. So this is the direction the charges actually move. And this motion depends on the electric field that I actually have and the potential difference of my battery. And it depends on it according to the following law. V equals the electric field times the distance that your charges are traveling. This is something we already know, and it can be applied here, where we can figure out an electric field, E, from the potential on the battery, V. So this is what physically happens inside of your battery. Your potential, V, whatever potential this battery has, say maybe a 9-volt battery, sets up electric current to flow through this, sets up charges to flow according to the electric field that it creates, E, times this distance that it's traveling, D, whatever distance your charges are going. And we have our negative charges, which are repelled from the negative terminal of our battery and flow around our circuit into a positive end. So these are my electrons flowing around in my circuit in kind of a counterclockwise direction. One of the things that I find most confusing about current, though, is that we don't look at what physically happens, we look at what we imagine would happen if positive charges moved. So if I have positive charges are going to flow around the circuit in a clockwise direction. They're going to go from the positive end into the negative end. So my blue here is the direction that positive charge would go. If positive charge actually moved. And this is a very important point to make. The direction the charges actually go is the direction that negative charges are moving. Negative charges are the only ones that move. Only negative charges move. But we define something called current as the direction that positive charges would go if the positive charge actually moved. So the current is the opposite direction to the actual direction of charge flow. And we define current very specifically. Current is equal to the amount of charge that's flowing divided by the time it takes that charge to move. We can denote current with the letter I, and in equation form, it's going to be equal to a change in charge inside of a circuit divided by a change in time, and this is going to be the definition if we're using discrete, very clear-cut currents. This doesn't always happen. Sometimes currents are changing as we're going around in a circuit. In this case, we need instantaneous changes, so current can be also defined as dq dt, the derivative of current, the derivative of charge with respect to time. So this would be the instantaneous current if we want to calculate that at any point. And we can figure out the units for current from the units for charge, which are coulombs, divided by the units for time, which are seconds. So current is measured in coulombs per second, which we give another term, we give another name to. We call these amperes. Or amps for short. To get some practice and some familiarity with working with currents and direction of current flow, I suggest you check up 7.1. Now, when I take a wire and I send current through it, there's something very specific that's happening inside of that wire. So I'm going to imagine blowing up a picture of a wire. Wire is just a long cylinder of some kind of conductor. And what's actually going on with the current is we have electrons inside of this. The electrons, they kind of bounce around all over the place. So I might have an electron bounce into the wall, hit the wall, bounce back and forth, bouncing all over the place, bouncing into other electrons, but constantly moving. And I have this happening with lots and lots of different electrons. I'll draw a second electron in here. Another electron bouncing all over the place. And what the current does is the current measures how much of these overall bounces are in one direction. And when we set up a current, we're forcing all the electrons to bounce into each other so that the overall bounce, when you add everything together as a vector, sends a current in one direction. The current gradually drifting in this direction, the electrons drifting, if you will, drift down this wire. They don't all move nice and orderly, they drift. They gradually bounce into each other with a motion in the direction of the current. So these electrons drift / collide in the direction of the current. You can read about this in your textbook. It's something called the drift velocity. And what happens with this drift velocity, with these electrons bumping into each other, all these collisions heat up your wire. You're colliding into the wall of the wire. That's going to heat it up. You can feel this when you're charging your electronics. Your charger gets warm. This is because of all of these collisions of the electrons inside of it. And these collisions, they kind of impede your electron flow. They slow down how fast your electrons can move. They impede motion. And the amount that these wires impede electron flow, we call this the resistivity of a wire. And we label this with the Greek letter rho. Now, the resistivity of different materials is different. Things that are better conductors have lower resistivities. But we really usually describe the resistivity in terms of something called the resistance. The resistance R is equal to the resistivity of your wire times the length of your wire divided by the area. So rho is resistivity, how easily electrons can flow along your wire. Better conductors have lower resistivities. L is going to be the length of your wire. And if we look at this equation, it kind of makes sense. If the length is really, really long, if L is really, really large, we're going to get more collisions, so we're going to have a higher resistance. We're going to lose more electron flow. All divided by A, the cross-sectional area of this wire. This also makes sense too. If you think about it, the area of the wire, the cross-section of the wire, if the wire is wider, if the wire has a larger radius, if it's a bigger circle, there's less chance electrons will bump into each other and cause the resistance to increase. And resistance, I call them the Monk units. Resistance units are called ohms. Now that we've defined both current and resistance, we can get to something called Ohm's law. The way that I like to remember it, because I don't like remembering fractions, I think there's room for confusion there, I remember V is voltage is equal to I times R. Your book describes this a little bit differently. Your book will give you the same equation for Ohm's law. I is equal to V divided by R. Notice that they're the same thing. They both give you kind of the same idea. If we analyze the book's version of Ohm's law, they give us the current. The current is the charge divided by the time. Is that what we have here? Well, V, the voltage, kind of tells you the amount of charge that you can have. Divided by R, R is how fast that charge can go, how well it's impeded, how much electrons flow, how many electrons flow. So it's kind of the same thing. It's kind of the amount of charge divided by how fast they flow. So it's the same basic idea. Very important physics equation to memorize, V equals I times R. Something that happens when we're talking about resistance is that it actually changes with temperature. And if I want to calculate this change, I can do it. The resistance inside of a wire will change, and that change in resistance will be equal to this letter alpha, which stands for temperature coefficient of resistance, times the resistance of a wire at some set temperature times the change in temperature. So I can compare the resistance of a wire at, say, freezing temperature to boiling temperature, and I can figure out how it's going to change. It depends on this alpha, which is the temperature coefficient of resistance. And you can do some calculations with this, you can do some problems in your book with this, but where this becomes really, really popular and very useful is with the concept of something called a superconductor. And superconductors are very, very cool, literally and figuratively. We'll watch a little demonstration, we'll watch a little bit of videos about this in class, but the superconductor is a special type of material. And this material is special because it has zero resistance. It's a material with no resistance. Below some certain temperature. So resistance becomes zero. If resistance is zero, that means no electrons are impeded from flowing. So electrons can move, current can move very, very well in a superconductor. There's no loss to heat. The collisions of electrons, they don't happen. No loss of energy to heat in a superconducting wire. One of the big goals of research physicists is to find something called a high temperature superconductor. If you could build some kind of power company, some kind of power line out of a high temperature superconductor, then you wouldn't lose any of the energy to heat from electron collisions when you take your power from the power plant to your actual house. This would make energy a whole lot cheaper, and means you wouldn't lose any energy along the way. So high temperature superconductors, they're going to be a big field in the future, and I think there's going to be a lot of good work done in this. Now, how do we practically use resistors? We're going to use resistors again in circuit diagrams. We can use resistors to change the amount of charge that's flowing inside of our circuit. And we can change that all using Ohm's law, using V equals I times R. Except we use it in the format that your book gives, current equals voltage divided by R. So using different combinations of voltages and resistances, I can get out any current that I want. This is what happens in your electrical outlets when you're taking the wall, which gives you 120 volts, and working it out so that it only gives maybe 10 volts to power your actual equipment. We use this kind of current delivery system, and we use these kinds of resistors to make things happen, to get out the currents and voltages that we want. In a circuit, a resistor has a very specific picture that we draw. The circuit element for a resistor looks like a long line that connects to a kind of tooth-shaped feature, followed by another line. This is the circuit diagram for any kind of resistor. And as I said, we can combine resistors in all sorts of ways to get out any kind of voltage, current, or resistance that we want inside of our circuit. And similarly to capacitors, there's two ways to combine resistors. We can combine resistors in parallel, and we can combine resistors in series. If we combine resistors in parallel, what does that circuit diagram look like? Well, I draw my battery, I have my wire come in, and it reaches this point where it branches out in two potential different directions. I draw my resistors, and then I finish off drawing the rest of my circuit. And what I see here is my current, my voltage going through this battery has a choice. It can go up or it can go down. It can take either of these two parallel paths. These parallel paths for the two resistances, resistance 1 and resistance 2. If I want to figure out what the total resistance inside of this circuit is, I can do that by doing the total resistance, R total. And I need 1 divided by that is equal to 1 divided by R1 plus 1 divided by R2. We get to this equation, the total resistance inside of a parallel resistor circuit, similarly to how we did the approach for capacitors, except you'll notice it's kind of opposite to capacitors. Capacitors in parallel add normally, resistors in parallel add a little funky. They have to add the reciprocal fractions. So we've seen what parallel looks like. We can also look at series resistor circuits. Circuits in series, you have your battery, you come in, and you hit your first resistor, and you hit your second resistor, and then you hit the other end of your battery. As I'm going around this circuit, there's nowhere else for my current to go, nowhere else for my circuit to go. It can't go up through a choice of the first or second resistance. So the resistors are in series with one another. One follows another. The total resistance in this case is going to be equal to the first resistor plus the second resistor. Resistors in series add normally. You don't have to worry about fractions with those. And if we use clever combinations of resistors in series and parallel, that's how we get any kind of current out from the wall that we want, using these combinations of resistors in series and parallel, and knowing that V is equal to I times R from Ohm's law. And you'll get plenty of practice solving some resistor problems.